Today we can discuss chapter 2, vector fields. First we define a vector. A vector at a point P belongs to Rn plus 1 is a pair V equal to P comma V. That P is a point in Rn plus 1 where V is again another point in Rn plus 1. Okay, so this can be considered as an element of, or pair V can be considered as an element of that Rn plus 1 cross Rn plus 1. Okay, this is a vector. Remarks on this definition: the vectors at P form a vector space denoted by Rpn plus 1. That means the vectors at P. Okay, the vector at a point P is defined as P comma V. V is again an element of Rn plus 1. And vector space is denoted by Rpn plus 1. That is the collection of all vectors at P. Then the dimension of clearly the dimension of this is n plus 1. With the addition, vector addition is defined as P comma V plus P comma W is equal to P comma V plus W. We will add only the vector part, the second component of the vector. And scalar multiplication is again performed using the second component. C comma PV is equal to P comma C times PV is equal to P comma CV. The set of all vectors at all points of Rn plus 1 can be defined as identified as a set with the Cartesian product Rn plus 1 cross Rn plus 1. Okay, at any point of Rn plus 1 we can define a vector. So set of all vectors at all points, okay, that is denoted by Rn plus 1 cross Rn plus 1. Okay. Rules of addition does not permit the addition of vectors at different points of Rn plus 1. That means if we consider two vectors, one is at P, that is P comma V, another is at some Q comma some W. So you cannot, we are not defining the addition of those two entities because they are different vectors at different points. Okay, this addition is defined only for vectors at a common point. Okay, similarly the scalar multiplication. So these are the remarks on the definition of the vector. Now you can define again dot product of two vectors and cross product. Obviously, cross product is defined only for the vectors in R3. Dot product can be defined for any Rn plus 1. So that is defined as V dot W. That V dot W is the dot product in the Rn plus 1. Okay, the cross product, V cross W is the cross product, but the cross product should be in Rn plus R3, not in Rn plus 1. Now we have definition of vector fields. Okay, a vector field X on U, that is a subset of Rn plus 1, is a function which assigns to each point of U a vector at point xp. That is, x is a function which assigns a vector at P. Okay, so x of P is equal to a vector at P. Okay, so this x of P is the vector part. Okay, for some, so this capital X can be considered as a function from P to Rn plus 1. That means x of P, this x of P is an element of Rn plus 1, and P is also an element of Rn plus 1. So this constitute a vector. This is the definition of a smooth vector field. A function f from U to R is a smooth if all its partial derivatives or of all orders exist and are continuous. Okay, this is just a property of a function. Using this property, we will define smooth vector fields. Okay, a function f from U to Rk, U is an open set in Rn plus 1. Okay, defined by f of P is equal to f1 of P, f2 of P, f2 of P, etc. fk of P is smooth if each component function fi is smooth. Okay, the first one is the definition of a smooth function from U to R. Using this idea, we will extend the definition to Rn plus 1. If we consider any subset of Rn plus 1 U, we can define a function f from U to Rk, and that is smooth if the components of those the function f is smooth. Okay, the smoothness of the components will be obtained using the definition given in this. Okay. Similarly, you can define gradient vector associated with each smooth function f from u to r. U is a subset of Rn plus 1. Unless or otherwise stated, this U is always a subset of Rn plus 1. It's a smooth vector field. Okay, this vector field is smooth if the components are smooth. Okay, on U called the gradient del f of f. Okay, then gradient del f is again a vector field. This assigns a vector at P in this manner: dou f by dou x1 of P, etc. Dou f by dou xn plus 1 of P. Okay, this assigns a vector at P. Therefore, this del f is defined as the vector field, and the components are smooth. Then we can say that this vector field is a smooth vector field. A smooth vector field defined in this manner is called gradient. Now we can define parameterized curve. A parameterized curve in Rn plus 1 is a smooth function alpha from I to Rn plus 1, where I is some interval in R. Okay, so this is the definition of a parameterized curve. So parameterized curve is a smooth function. Smooth function means its components are differentiable. Partial derivatives are differentiable, or components are differentiable. Since this was a function from I to Rn plus 1, this I is a subset of R, obviously. This alpha has n plus 1 components, say alpha 1, alpha 2, etc., or x1, x2, etc., xn plus 1. Clear? If these components are smooth, then we can say that alpha is smooth. Such function is called such smooth function is called a parameterized curve. Okay. One interesting example is a velocity vector. If we consider a parameterized curve alpha, then alpha dot, that is defined as alpha of t comma d alpha by dt. D alpha by dt is the derivative. This constitutes the components of the derivative. Some components of the derivative will be equal to this d alpha by dt. Okay, so that is dx1 by dt, etc. Okay, this is an example for smooth vector field, or a vector field, velocity vector. Now we can define integral curve. This is an important idea. What is an integral curve? A parameterized curve alpha from I to Rn plus 1 is said to be an integral curve of the vector field x. Okay, on the open set U in Rn plus 1, if alpha of t belongs to U and alpha dot t equal to x of alpha of t for all t belongs to I. That is, if we consider parameterized curve from I to Rn plus 1, this is said to be a integral curve of this vector field x. So first thing you remember is that x is always defined on U. Okay, that is already given. Then only we can say that a parameterized curve is an integral curve of that x. Clear? So a parameterized curve alpha is an integral curve of the vector field x if the image of alpha, that means alpha fully contained in U, and the velocity vector of alpha coincides with this vector field x. Okay, if x is the velocity vector field of alpha, then we can say that that is the integral curve. Then we have a remark: alpha has the property that its velocity vector at each point of the curve coincides with the value of the vector field at that point. That is nothing but the definition. Then we have a theorem. Let x be a smooth vector field on an open set U in Rn plus 1, and P belongs to U. Then there is an open interval I containing 0 and an integral curve. Okay, then the integral curve means that should be a parameterized curve, and the image should be fully contained in U, and the velocity vector field coincides with the x vector field x. That is the condition. then we can, if this is the case, we can find or there exists at least one integral curve alpha such that alpha of 0 is equal to p, and we have some kind of uniqueness is there. If beta is another integral curve of x, the same x with beta of 0 equal to p, with the same property of this alpha, then that beta is same as alpha in the common interval, okay, or the domain of the interval beta is always contained in alpha. Those such integral curve exist. That is the statement of the theorem. So this asserts that there exists a unique maximal integral curve. Okay, so for any integral curve beta, that the domain of beta should be contained in I. Okay, that means in that sense we can say that this alpha is the maximal integral curve. Okay, any other integral curve, domain of any other integral curve contained in the domain of the alpha. The proof is very easy. When you equate these condition, the condition of the integral curve, if x of p is the smooth vector field and alpha is a parameterized curve. So this the vector field is defined as capital X1, capital X2, etc. And the parameterized curve is integral curve is parameterized curve is defined as small x1, etc. Small x1 plus 1 t. In order to be this alpha of t is the integral curve of x, we need to get this condition: alpha dot t, velocity vector field should be coincided with this x of alpha of t. From this you can solve this one, because alpha dot t is dx1 by dt. So that is the left hand side. Left hand side is a vector. At the point alpha of t, this alpha dot t assigns dx1 by dt, dx2 by dt, and so on. Clear? So this is d by dt of x1 of t. That is the thing here. That should coincide with this x of alpha of t. X of alpha of t is x1 of alpha of t. What is alpha of t? Alpha of t is this x1 of t, x2 of t, etc. So when you solve this system of differential equations, you can get the solution, or if this if there is a solution for this differential equation, you can say that alpha exists in this case. Clear? So that is nothing but the existence theorem of differentiability. If all the partial derivatives are continuous, then the system contains this system has should have a solution set. Then from that you can say that this alpha of t is the integral curve which satisfies this condition. Okay, if there is another solution, you can consider the union of the intervals of the solutions. Then you can get the maximal integral curve, and the second condition follows. Okay, this is the idea of the proof. So you need to go through the proof given in chapter 2. The entire proof is given in chapter 2. So you need to verify all those. This is the key idea of that. Okay, and another important thing is how to get this maximal curve. If there exists two such solutions for this system of differential equations, say alpha 1 and alpha 2, and alpha 1 is defined on some I1 and alpha 2 is defined on another interval I2, both contain 0, so that should be a overlapping intervals. So you can collect the union of I1 and I2. Okay, you can consider alpha 1 I1 and I2, union of I1 and I2 as the domain, and in I1 define this alpha 1, and in I2 define alpha 2. Then you can in that using that definition you can define a new function alpha on I1 that is that coincides with alpha 1, in I2 that coincides with alpha 2. So you can define this alpha in I1 union I2. If there exists another solution of this differential equation, then adjoin that with this by extending the domain I1 union I2 to I1 union I2 union the domain of the third one. Okay, then collect all such solutions of this differential system of differential equations and define a function alpha in the union of the domains of those solutions. Okay, that will give this alpha. Then that alpha should have this property. Okay, that in that sense we can say that alpha is a maximal integral curve. So this is the chapter 2. 2. This is the last theorem of chapter 2. So you need to try the exercise problems. If there is any doubts regarding those problems, we can discuss in live interaction.